Have you ever wondered how a machine generates text that sounds, well, incredibly human, like it's actually in there thinking? If you've ever been amazed, or maybe even a little bit unnerved, by what's happening under the hood of today's language models, you are in the exact right place. Welcome to this explainer. Today we're going to completely demystify the core architecture that powers modern large language models. We're starting right from the big picture, making it super accessible even if you have zero background. And then we'll travel all the way down to the strategic architectural shifts that are literally rewriting global industries today. Let's dive in.
Here is our roadmap for today. We'll be building our understanding in three distinct layers. Number one, the AI memory problem. Number two, the transformer framework. And number three, the new AI paradigm.
Okay, let's kick things off with section 1, the AI memory problem. To start simple, we really have to look at the historical roadblock of early AI systems, which was essentially short-term memory loss. If you track the evolution of neural networks, you see this crazy progression. Back in the 80s and 90s, we relied on sequential models. These processed text literally one word at a time, but they had a fatal flaw. Imagine you're reading this long, complex, epic novel, but by the time you hit chapter 3, you've totally forgotten who the main character is. That was the reality for these early models. In a long paragraph, the context of the first few words would just slowly fade away. So in the 90s, researchers introduced selective memory models, trying to teach systems to selectively remember or forget things to save space, but it was highly complicated and painfully slow. Then, in 2017, a landmark breakthrough introduced something called the attention mechanism, and it completely changed the game forever.
This right here is the perfect way to visualize that massive shift. Early sequential AI models were essentially reading text by looking through a tiny, moving peephole. They could only see one word at a time, missing the broader context entirely. The attention mechanism? It flipped a switch. Suddenly the lights were on. The machine could evaluate every single word in a sentence simultaneously and figure out exactly how they all relate to each other, no matter how far apart they were on the page. Boom, the memory problem was officially solved.
So, the machine can finally see the whole page at once. Awesome, right? But this brings up a really fascinating question, and it moves us into our intermediate framework layer. Because to truly grasp this architecture, we have to ask, how does a purely mathematical model know the difference between crane, the flying bird, and crane, the heavy construction equipment? To a machine, it's just a string of letters.
Which brings us nicely to section 2, the transformer framework.
Let's pull out the microscope and examine the exact mechanical journey your prompt takes to actually become machine understanding. Unlike us humans, who naturally use context and intuition, and let's be honest, a healthy dose of guessing, to figure out what a word means, machines just can't do that. They have zero life experience to draw from, so they require a highly structured, strictly mathematical translation to make sense of language. Literally everything must be turned into numbers.
Any sequence of text you input into an AI has to go through a strict three-step data pipeline to be formatted for the transformer engine. Think of this as the definitive translation layer between human thought and machine calculation. Step 1 is tokenization. Step 2, token embedding. And step 3, positional encoding. Let's break these down.
Step 1 is tokenization. This is simply the process of breaking down your text and assigning it a unique index number from a massive predefined vocabulary dictionary. So the word crane might be assigned the ID number 4052. But here's the catch. A simple ID number doesn't tell the machine what the word actually means. It's literally just a barcode. And just like scanning a barcode on a box of cereal doesn't tell the grocery store scanner what the cereal tastes like, an ID number doesn't give the machine the definition. To actually understand meaning, we absolutely need step 2.
Now take a look at this massive number, 768. In many foundational models, this represents the dimensions in a single token embedding. This is where the magic happens, and meaning is born. Imagine the model asking 768 entirely different semantic questions about that single word, crane. Is it alive? Is it made of metal? Is it heavy? Does it fly? Each answer gives the word a specific mathematical coordinate, locating it precisely in a vast universe of meaning.
And that is the token embedding phase. By mapping words as vectors in a multi-dimensional space, the model mathematically plots semantic relationships. Think of it like a giant galaxy of concepts. Words with similar meanings are physically plotted closer together in this deep space. This is exactly how the machine captures nuance. Through the surrounding context words in your sentence, like feathers versus steel, the model zeroes in on exactly which crane you're talking about. It navigates the map, and it finally grasps your true context.
But wait, we have one final step to make this work. Because we're processing all these words at the exact same time, remember, the lights are on, we see the whole page at once. The model actually loses track of the word order. It knows what the words mean, but not how they're arranged. So we apply positional encoding. This acts as a chronological timestamp. Without this crucial final step, the AI would just see a jumbled bag of floating concepts instead of a beautifully structured sentence. And with that, our mathematical translation is completely finished.
All right, moving into our final layer. Section 3, the new AI paradigm.
Now that we understand the incredible mechanics under the hood, what does this mean for the advanced practitioners, the leaders, and the strategists watching? How does this impact your enterprise tech stack? Well, it starts with a fundamental mindset shift regarding parameters. When you hear a new model has 70 billion or 400 billion parameters, please don't just think of them as simple data points or static storage space. Think of them as distinct capabilities, complex topics, and deep reasoning skills acquired during massive pre-training. It's not just raw data, it is learned behavior.
And because of that incredible pre-training, state-of-the-art models actually freeze the encoder layer, the core language understanding. It's already baked in. It's done. This means we no longer need to train foundational models from scratch just to get them to understand human intent. We'd leverage these massive pre-trained capabilities via decoder-only architectures. You don't need to teach it English from scratch, you just need to teach it your specific business logic. You are essentially renting a supercomputer's brain that already knows exactly how to think.
So the crucial point is how this shifts your entire professional workflow. Just look at the stark night and day differences in this table. This completely renders the traditional paradigm of custom-building predictive models obsolete for so many modern business use cases. Instead of spending months and hundreds of thousands of dollars doing intense, from-scratch machine learning, you can achieve superior results in literally days through agentic AI. That is a massive shift in ROI. You are shifting your core focus from predictive classification to high-level reasoning and orchestration.
I want to leave you with this final, provocative thought. Your role in the modern workforce is fundamentally changing. The absolute biggest takeaway to act on right now is that your job is no longer writing the complex algorithms of the past. Your job is now directing the reasoning engines of the future. You are an orchestrator of intelligence. So how are you going to use these powerful pre-trained frameworks to solve your biggest challenges tomorrow? Think about that, and I'll catch you in the next explainer.